Today's show is sponsored by Xilinx, the world leader in programmable technology. Xilinx field programmable gate arrays give engineers a blank chalkboard on which they can quickly and effectively design products with a high degree of flexibility. Xilinx FPGAs are enabling advanced technologies throughout industries such as consumer electronics, medical, aerospace and defense, and security. Xilinx continues to deliver breakthrough programmable technology to the global market. Xilinx. Last time on the Analog by Design show.
At high speeds, you really need a buffer amplifier. Now, when you have a very high-speed A to D converter putting out a very large amount of bits per second, what do you do with it? You can't just get it all into the computer because computers cannot accommodate all that much information. So you need something very fast, such as a write-only memory, the WOM. And Xilinx has come out with an FPGA called the Vertex 4-LX15, which is suitable for interfacing between a fast data flow and a computer that isn't quite as fast as that. You really need some careful control of the power supplies because you need all sorts of different voltages and different sequencing of voltages. They have to be very compatible.
Ian, what he had to do was take the data from the analog in, get the digital data out of the ADC, and feed it to the computer for analysis through a USB.
Effective number of bits is actually derived from SINAD, which is the signal-to-noise ratio and distortion performance of the converter.
Different forms of distortion give you different appearances in that spectrum. If you have nonlinear distortion in the amplifier, it would show up as second, third harmonics showing up in that picture. So if you had random clock jitter in the sampling clock, it shows up as white noise, or some kind of noise, that's been added to the signal. So that would raise generally the noise floor underneath the spectrum of the signal, but not affect necessarily the amplitude of the different harmonics. You'll notice the board is partitioned into two pieces. The top half is the analog section. That's the A to D converter itself. The bottom half is the digital section. That's the Vertex chip going out to the bottom.
From the high-performance analog IC design and manufacturing capital of the world, it's National Semiconductor's Analog by Design show. Here's your host, the guru of analog, the one and only Bob Pease.
And here we go again with National Semiconductor's Analog by Design with Bob Pease as host. That's me. And we're going to talk some more about what's all this high-speed data transfer stuff. And part two, we originally talked in part one about things that ought to work, and in part two we're covering things that do work and things that don't work. We actually checked out things that do and don't work. Now we're going to turn this over to Carrie Esco from Avnet, who will tell us more about today's show and introduce more information, and one of our guest speakers.
Thank you, Bob. In these sessions, we'll explore the complex and challenging issues surrounding high-speed data transfer and demonstrate how this can be accomplished by examining the problem step by step and block by block. We have with us today the author of High-Speed Digital Design, A Handbook of Black Magic, EDN columnist, and signal integrity wizard. Please welcome Dr. Howard Johnson.
Thank you, Kerry.
Paul, who else are we going to get introduced right now?
Well, today we have Panch Chandrasekharan from Xilinx. He's a marketing manager there. Not just a marketing manager, he was an IC designer previously. He's designed 2.5 and 10 gigabit per sample chips for telecom. He has an MSSE from the University of Central Florida. On my left is Ian King. He works in our DCS group. That's our data conversion systems. Ian went to Nottingham Trent.
Right, Nottingham Trent.
In England.
Yep.
He has a bachelor's degree, and he's a senior systems engineer at National, and he's got over 10 years experience in system-level board design. You'll see this beautiful board he's done.
Okay. Now, we originally last week talked about a lot of things to do with signals that are going into a high-speed A to D converter. And we talked a little bit about the preamps that were useful to get the signal under control. And we talked about how to get a FPGA, a field programmable gate array, to transfer the signal out of the fast A to D converter into the medium speed computer. And we did say that you needed a lot of wires to do it. Hopefully short, straight wires. Now we did mention about power supplies and power supply controllers that help us get the right power into the computer, the FPGA, the A to D converter, and not goof things up, which is the main point. Now we're going to go a little bit in a different direction today also, because we're going to talk about these wires. And what if these wires weren't nice, straight, short wires, but what if some of them were bent and warped, and some of the clock talked to the signals, and what if some of the outputs talked to the other parts of the signals? Wouldn't that be messy? So I think, Howard, we're going to hand that over to you. Which part of this do you want to work on first?
Well, I think there's several things that we can attack. One thing that I'd like to do is to talk a little bit about the power system, how it affects the performance of the overall system.
Sometimes power gets put off till the last minute, and you test your system with lab supplies, and then you get the real switcher, and everything goes to heck. What kind of problems do people have to look for?
Well, there's two things I can think of. One is the way in which the power noise directly goes to the input of the system and creates crosstalk. The other aspect is how the power supply noise gets through the power pins of chips into the chips and then affects system performance.
From the noise perspective, Panch, what other things come involved with the power system?
Okay, a clean power supply obviously is very important, like we just talked about. From an ADC point of view, Ian, a noise in the power supply can affect your noise floor, which eventually impacts your total effective number of bits, which is your figure of merit. On the interface side, noise in the power supply can also affect your signals in the form of jitter, and again, that goes on to affect your timing margin. So minimizing jitter is key in interfaces, and by extension, I guess, maintaining a clean power supply can impact the amount of jitter you have in interfaces.
Oh, what was that article that you had in of how to design power supplies for FPGA systems? Have you got that here?
Yeah, I do, yeah. We have...
drag that out, please. We'll
Yep.
set that right down here. Let me move my junk aside.
This is a national guide for the layout of switching power supplies.
And that is AN 1149 by Clint Jensen in October of 1999. And if you say, I don't know how to design a power supply for a system like this, fine, but you read this book and you're going to start learning to make that power supply real easily and real fast. So this is very valuable. How many pages is it?
It's just a couple. It's just a layout.
Couple pages,
Daylight
yeah, 3
guideline.
pages.
Yeah, very straightforward.
Good.
Yeah.
Was there another one?
Yeah, and there's also the National Design Guide that we
okay.
we suggest specific.
How many pages is that?
It's quite a big. That's a 24-page.
Oh,
booklet,
very good.
So, yeah.
Wow, that's a lot.
But you can download that off of
Oh, you
our
download that
website.
off the web.
That's
I'm
right.
going to download this and learn about it because it's the kind of thing I should know too. This is CC more up to date. So summer of 2005. So it's a little bit beyond, and it's got more modern devices in there.
Right.
Does it recommend particular power supply regulators and?
It does, yes. And again, you have to work with.
Oh yeah, pages and pages of fine print. If you need to know how to design it, boy, this is a good place to start. Okay. Have we covered most of the power supply questions?
I guess, Howard, do people putting linear supplies in after a switcher? Or,
Yeah, I see that a lot as a way to make a tightly controlled power source, especially for chips where you're worried about low frequency jitter. Now, the switching power supplies, for the most part, operate in the couple of hundred kilohertz range. If the power system is going up and down at that speed, it may create a low frequency jitter, but in a lot of cases, you expect your receivers are going to track that jitter, so that doesn't cause a problem.
Oh, okay.
In some systems, though, ones that are designed to go for enormous numbers of long strings of ones or zeros in a row with no transitions and still hit dead on the mark at the next bit baud cell, in that kind of system, you've even got to get the low frequency jitter way down, and that's where I see linear regulators being used. Okay. I have a question for you. Applications that I see a lot of, people get a regulator, they put it on the board, they get this chip, that chip, the other chip. Every chip they buy has a different recommendation for the power system. So they glom them all on there, and I'm beginning to hear reports of people that put so many capacitors around their system, it makes the regulator go unstable.
Yeah, that's been...
What do we do about that? Do you have recommendations that say, here's the minimum amount of ESR you have to have or something in order to keep the thing stable?
People are using some low dropout regulators, and some of those are quite touchy about needing a capacitor a load capacitor with some RS. And we are trying to put that very carefully in our data sheet that a guy can't say, you didn't warn us. If we say 10 to 100 milliohms, you put that in, it's going to work. If you don't put it in, it's likely to oscillate. So it's pretty clear these days to have low dropout regulators that people like for popular functions or for switchers, that it's well defined what the RS and the load capacitance must be.
I worked on a handheld product where we had to have ceramics for size and form factor, and we put discrete, tiny, 100 milliohm resistors in series to create series resistance. It sounds kludgy, but it works, and everything met the spec, and you still have a fairly low impedance source.
I'm seeing applications in the digital world where with the bypass capacitors themselves, the ones of the array all over the board, they have a certain inductance. The planes in the power and ground planes have a certain capacitance. And between those two elements, they can resonate. Now, the lower you make the ESR of the capacitor, the less resistance it has, the higher the peak of the resonant hump. So there's a desire in a digital system, really, that's another place where you want a capacitor that has a certain minimum amount of ESR. And what I'm not seeing is I'm not seeing the capacitor manufacturers respond to that. I'd like to see parts that had a bigger ESR, not a smaller one.
Put some damping in.
Because then the capacitor couldn't resonate if it wanted to.
Right.
Well, sometimes you put in 200 microfarads of tantalum, and that has enough ESR to damp out the ringing. And as I said on page 34 of my book, yeah, you can add all the capacitors you want, but sometimes you want to add just enough of one type and not too much of the other. Also, as Paul pointed out, you put a few milliohms of chip resistor in series with capacitors, and that helps damp things out. Even more predictable than tantalum.
Do you have cases where people are trying to kill high-frequency noise, let's say, like I have, where they use a big capacitor, a physically big capacitor, and a big value, when really a few picofarad, if you look at the actual curve, the impedance curve of the capacitor, they're better off using a smaller numeric value to get a lower impedance at the actual frequency. And it's all analog. It's tough stuff.
The main thing that matters for digital systems with regard to the bypass array is the inductance of each capacitor and how many you have. And so we shoot for the lowest inductance we can get by using the tiniest package that our manufacturing people will let us use. We put the vias straight on the sides of the capacitor pad, straight to the power and ground planes. No resistor, because that would add inductance, which is why you got to have the resistance in the capacitor if you're going to have it. But that's the lowest inductance format, and that's the most important thing to do. If you had a 0.1 microfarad and a 0.001 microfarad in the same package, they got the same inductance. They had the same high frequency performance. The exact positioning of the zero isn't doing anything special in a digital circuit that's very helpful.
Okay. Good stuff.
Yeah, those are good points. And life ain't simple. And anybody who says, I wish life was simple, is wishing himself out of a job, because life ain't simple. And that's one of the reasons we still have jobs, because life ain't simple.
Is there a lot of capacitance between planes? Because I've been told, you hardly get anything. And people think that, I'll use plane capacitance, but a real board.
It's very helpful. There's a certain frequency range where the bypass cap array is doing most of the work. There's a range below that where it's the bulk capacitors, the big 100 microfarad guys doing the work. Range below that where it's the voltage regulator module itself. And way up on the top, it's all about the planes.
Really?
The transition from the bypass caps to the planes in most boards happens somewhere in the several hundred megahertz territory. Low is 100 megahertz, high is a gigahertz. Somewhere in that range is where that trade-off happens. Above that point, the planes are all you got.
Okay, great.
Yeah, you don't have to worry about ESL issues when it comes to planes.
Two pieces of copper.
Okay, we finished off all the power supply topics for this kind of system. We're going to go over to the lab shortly, but before we go, Paul, what's our next item?
Okay, our sponsor today is Avnet. We're going to have a little break here and learn about Avnet, then we're going to go over to the lab.
You can relieve the stress of time-to-market pressure with a single call to Avnet. We'll help you get your idea off the drawing board and to market quicker and more cost-effectively. Working with Avnet gives you access to highly knowledgeable field applications engineers and the most sophisticated development tools and technical education available. Avnet's deep understanding of National Semiconductor's high-performance analog portfolios, including power, amplifier, interface, and data conversion products, as well as Xilinx FPGAs and CPLDs, allows us to help our customers bring a wide range of performance and cost-sensitive applications to life. So contact Avnet today to find out how you can gain an important competitive advantage in the product development race.
Hi, we're back here in our lab segment with all this cool test equipment. And Kerry, what do you got there? It's a board layout, right?
Yes, one of the areas of the layout that looks most interesting is this section. Now, I was wondering why the trace lengths seem to be so carefully controlled.
What we're looking at there, in the context of the whole board first, is that inputs come in over here on this side, outputs are going out on the right-hand side, and in the middle we see the A to D converter here, this big green square, and that's the Vertex 4 chip where we're pumping all our data. These traces that you pointed out are the things that connect the LVDS lines from the A to D converter over to the Vertex 4 chip. They go on the bottom, there's some more on the top, and then there's these interesting ones that make U-shapes here in the middle. Now, what Ian's trying to accomplish with that, if I understand it right, is he's trying to make all the traces the same length.
Correct.
The reason we want to do that is because we have a big parallel bus. We only have one clock signal going across to the Vertex 4 chip, and so all the data lines need to arrive at the same time so that they're all sampled by the same clock. Now, how accurate do they have to be? Well, it depends on the length of the clock interval. One rule of thumb that I find quite handy in these situations is to remember that on FR4, a trace of 6 inches length has a delay of 1 nanosecond. So if I think of a 1 nanosecond rising edge as it slides down the trace, at every point, if I took a snapshot in time, that signal would be 6 inches long. If I dealing here with signals of about a half nanosecond rise time, that's 3 inches. And if we want to have the signal's delay controlled to within a small fraction of a rise time, that's the usual standard for a bus, then we are shooting for a difference in delay from trace to trace of no more than a small fraction of 3 inches. That'd be like a couple tenths of an inch, might be okay.
How long are these traces here, Ian?
The total length is about 6 inches.
About 6 inches, so that's
6
right
inches
about...
6 inches on that scale, and this is half scale?
Yeah,
Right.
so I think it's
Okay.
about a 3-inch trace
Right.
overall is what it looks like to me. Yeah. And some of the traces, you've done an interesting pattern. If we can get in really close here, you can see you come down, you go over, and the way that bend is done is this trace is short, so it has a short vertical run but a longer horizontal run. This one goes longer vertically but not as far horizontally.
Right.
It's as if you had taken a ribbon cable that was straight, and you know you can fold it to make a right angle bend.
Yeah.
And they're all the same length when you do that. It's a beautiful pattern.
Now, you laid this out in Allegro, right?
Allegro, correct, yeah.
Now, did they miter corners? Was that necessary?
You
in
can
this
mount the
design?
corners if you wish, but all the LVDS was just hand routed, and we just used the length matching tool to perfectly get all those lengths within 40 mils of each
You
other.
were within 40 mils of each other. That's pretty close.
Yeah.
Now
this
there's
would have
there's an alternative way that we could have done the design. Instead of matching the traces, which takes design effort, we could have used perhaps the chip sync feature that's built into the Vertex 4 product.
That's right.
Punch, what does that do?
Yeah, like we talked about earlier in the show, chip sync basically allows you to adjust your delays based on your data. So if you have a wide parallel data bus like you have here, you can independently adjust the delay of each individual channel so you can perfectly align it to the clock so you get your optimal bit error rate for your interface.
And it'll learn. You can just lay the board out the way you like.
That's right.
Now
I mean, you don't want to go
Crazy.
too crazy.
What different? I mean, could you route these here straight and have a 3-inch trace here? How
much can it
many
tolerate?
centimeters can you compensate for?
Okay, I'm trying to remember this, but you have pretty good tolerance. You have, I think, a few nanoseconds of tolerance.
Oh,
even.
wow, that's
So,
great, sure.
So maybe as much as plus or minus half a bit cell in the system easily you can
right.
accommodate
That's right.
and still be able to clock accurately. Now you asked a question, Paul, about mitering corners. Were you thinking about the effect of right angle bends that
Yeah.
might happen to those traces? I've heard a lot about that. From my friends in the microwave business, they worry about right angle bends.
Right.
And I looked into that one year to find out if there's any truth to the rumor that a right angle bend can hurt you. And here's what I discovered. There's 3 things that are different between a microwave application and the kind of stuff we're doing. The first thing is we're only at 1 gigahertz, not 70.
Right.
they're at least 10 times faster than we are in terms of the carrier frequencies used in microwave design. So they're 10 times more sensitive to small perturbations. Next, the microwave folks tend to cascade things. They'll take one signal, they go through an amplifier and a filter and a mixer and a this and a that, and imperfections in all the stages add up. But what we do is we take a signal, we put it through a gate, we regenerate a fresh, brand new signal at every stage.
Okay.
So things don't add up for us in the same way. And the third thing that's different is on this board, the traces are tiny. What's your trace width, Ian?
4 mils.
4 mil wide traces. On a microwave design, 50 mils, 100 mil wide traces in a lot of cases. Huge traces, way up off the plane. So they're still 50 ohms, but they're huge and wide.
Right.
The reason we do that is to lower the skin effect loss on those traces. If you're trying to get an amplifier that's flat within plus or minus 0.1 dB at high frequencies, even tiny losses matter. So they're using huge fat traces at very high frequencies, and they're very sensitive to losses. And the last thing, so multiplying those 3 factors of 10 together says they're about 1,000 times more sensitive to little tiny lumped element capacitances than we are. Now the reason I mention lumped element capacitors is because that's what the right angle bin does. When you go around a right angle bin, the trace is where it's squared off. You might imagine it gets a little wide as you go around that corner, doesn't it?
Right.
It looks like some extra copper hanging in the corner.
A miter kind of looks like it's reflect. Somebody said over 300 megahertz. Think of it like light coming down and reflecting, and you want the wavelengths to add up and be coherent across that boundary. But
I think of it much more as just a lumped element capacitance hanging in the corner.
Okay.
And the amount of capacitance for Ian's trace width is about 0.01 picofarads. 1/100th of 1 picofarad. 100 times less significant than a via.
10 femtofarad.
Tiny.
Yeah.
It's 10 femtofarad. Now, if it was 1,000 times bigger, if it was 10 picofarads, we'd worry about it. It'd be killing us. But if it's 10 femtofarads, for our designs with narrow traces at a few gigahertz, regenerating the signal every stage, we don't worry about right angle bins. They don't hurt. Electrically, there's no reason why you can't do them.
Oh, that's great to know.
Now, mechanically, I have heard some complaints that if you have one trace with a right angle bin, in the old wave soldering approach, when you used to take the board and it went over this wave of melted solder pot and solder splattered everywhere on the board, you get a solder ball caught in that corner. And if there was another trace next to it, then you get a short. And so it was a yield consideration. So people said, well, don't have right angle bins because they attract solder balls.
Right.
We do reflow soldering now. We're not using the wave solder. In high-speed electronics anyway, with lots of pins, we're doing reflow. The solder balls are not nearly the issue they were before. I can't see any reason why you could not use right angle bins for routing traces like these.
Oh, that's great to know.
Now, if you say, well, you're only going to use 45s, it doesn't hurt anything.
Right.
But sometimes if you have the flexibility of using right angle bins, it helps a little bit. So I like to keep that in my bag of tricks.
Yeah, I use OrCAD. It'll do an arc, but it will not miter. And it's great to know now that in these frequencies still I can do board work in that till Allegro like the hardcore people here. But that's fascinating. Did you want to look at the board and talk about some other applications here? Or?
Yeah, there's a lot we could look at on this board. One of the things that I wanted to ask about was just the fidelity of the signal tracks coming in and making their way into the ADD converter.
Sure.
And one of the ways that I'm used to looking at that is to use a time domain reflectometer. We send a signal into one of these channels and we look to see what bounces back. And that's what I believe Ian has got set up for us today.
Yes, indeed. We have.
It's on this piece of equipment right behind me. And Ian, tell us what we're looking at here.
Okay, so we have the TDR Tektronix oscilloscope set up. We connected a single channel into the analog Q channel input of the capture board. And we have the TDR sending a pulse out on the cable. And then it's the pulse reflection is coming back and it's listening. And what we see on the screen is...
So this first step, this is when the step begins.
Right.
Yeah.
And these little glitches represent the glitches inherent in the connector coming right out of the front of the equipment. After you get into this nice SMA cable, it's a consistent 50 ohms for a considerable distance. Now on this scale, an inch is about that long. So that's in 1 inch, that's another inch. We're about 6 inches away from the beginning. We get to this big old glitch. That would be the connectors, I think, at the front end of your PC board.
Right.
Now, one way to check and make sure that we know what we're looking at in this picture is to take a little bit of metal and touch it onto one of the traces on the board and see where it makes a glitch in this diagram. So, Ian, where are you touching right now?
Right at the ballon.
Right at the ballon. So you come through the connector, onto the board, into the ballon, and it's making an effect. Oh, there we go. Yeah, on and off. That's good. We can see where that effect is taking place. Is there any way you can get closer to the connector?
Not exactly now.
How about further away from the connector?
Yeah, we can go further away.
Okay, let's
Go to the
try
other
that.
side of the ballon.
The other side of the ballon. And we can just begin to see something happening over here, just after the ballon location. The idea with this test is that by touching the board in different places, you can tell what spots that corresponds to on this TDR waveform, and the waveform tells you whether the impedance is too high or too low at that spot. Now on this trace, the glitches look pretty significant, but really, this is done with a very fast rise time. How fast is this thing?
7.5 picoseconds.
7.5 picosecond rise and fall time. So even a tiny little imperfection over a very short period of space would create a big glitch on this picture. But what happens with the sort of rise times that we really have in your system, we were testing with, I don't know, let's say a 500 megahertz input. That takes a nanosecond to go up and a nanosecond to go back. It's a 1 nanosecond rise time. It's 6 inches long. That rise time is so long compared to the length of this TDR glitch that slow rise time will essentially average out everything in the glitch area. So as long as the total area under the positive and negative parts of that glitch are the same, it'll be electrically transparent at a nanosecond rise time. Now it looks to me like this one actually has a little more area on the positive side than the negative side, so I think even at 1 nanosecond you might see a small positive reflection from that could be worth trying to shave down in your next version of the layout.
Sure.
Ian, have you got any ideas for what you would do if you wanted to make the impedance a little lower in that area to bring down that reflection coefficient?
Yeah. I guess you could widen the trace a little bit.
Yeah, widen the trace. Perfect.
Yeah.
That works. Or even just right around the connector. Bigger pads on the vias.
Right.
Bring the clearances closer to the pads.
Sure.
That works. Make a bigger via hole. That might work. So a lot of things you can do to make adjustments in these little tiny impedance discontinuities.
Do you accept the rule of thumb I've been using that for 50 ohms, you go double the width of the trace down to the ground plane? So if you have 4 mil traces, that must mean it's 8 mils down to the ground plane. Is that?
Oh, close. I think it's the other way around. You said, if I heard you right, you said twice as wide as you are high. So 4 mils wide, 2 mils high would give you roughly 50 ohms, not taking into account the thickness of the trace.
And that's FR4.
You know, on a material with a dielectric constant of about 4, it's roughly how it works out. It's not exact, but it's a good starting place for thinking about it. If the trace is maybe 10 mils above the board, 20 mils wide, the thickness is insignificant, and you wouldn't worry about it. If you shrink down to 4 and 2, you'll notice that the thickness of the trace, about 1, is significant compared to the geometry, and so the impedance would be lower than you might think. And I'm guessing this board is probably 4 mils width and maybe, I don't know, 3 mils high or something. Is that about what you've got?
Right, yeah.
And then the solder mass changes. It's a dielectric, right?
Yeah, the solder mass can change the impedance. If it is too thick, you should really notice it. The thinner you make it, the less of an effect it's going to have on overall impedance.
So be ready to spin it a few times, I guess, is the
One more time, hopefully. That's it. Yep.
That's for any design of this caliber, any high speed.
I think it's a good idea for engineers to plan that if they're going to do a high-speed design, don't assume that the first one is going to come out perfectly. Now, this doesn't mean, what I'm saying is 2 passes are required, almost every high-speed design, to get things perfect, to get instrumentation quality, which is what you want. To get it to just work, this seemed to work the first time, great. But if you want it perfect, you need 2 passes. And what I counsel people to do is to think early in their project, what things do they think might go wrong, and make a test board that tests just those things. You don't have to have the design finished to do that.
Yeah, just
you learn a lot of information. You can incorporate that in your second run, and then you're golden. Sure. In fact, in a large company, I think what works the best is organizations that talk about what they're going to do for their test boards. Some signal integrity groups get together and they meet by conference phone, every month, and say, who's got a board going out for fab?
Right.
What tests can we do? And they think up things they can try to see how the world really works.
Oh, that's great. And then, of course, this board really helps our customers because they're getting a whole system where they're getting real bits out of it. And then we'll help them with their designs if they need help from our applications group. And the board's on the web, right? I mean,
It's available today.
Oh, great.
And we have them in stock.
Yeah. Avnet will get them to you. That's great to know, as always.
Well, have we covered just about everything? Just about everything. Thanks very much, all you guys. Thank you for all the visitors for dropping by. Thanks, Ian. Oh my God, we're almost through with. Thank you. Bye-bye.
Bye.
Bye.